Okay, in this video, I'm going to go over chapter 12 on recursion. I had the COVID booster today, so there's a chance I will be fuzzy-headed or have brain malfunction or a headache or may not even be in class on tomorrow, Friday. So I'm going to make this video just in case, okay? If I am there in class, then this will just serve as a kind of a reinforcement of that, okay? So chapter 12 talks about recursion. Recursion is defined as a function that calls itself. That's it. Recursive function is one that calls itself. Okay, so let me make sure I'm sharing the right thing here. Looks like I am. Okay, so let's take a look here at a sample program. This one is called Endless Recursion. It's on page 577. And this is a trivial, not very good example, but you can see what's going on here. So we have a new file. That's where you can see it, hopefully. Okay, so on this one, we have the comment, this program as a recursive function. Okay, so we have our def main as always. Okay, it's going to call the message function. Okay, we have our def message that is going to print. This is a recursive function. Okay, that's it. And then it's going to call the message function again. Okay, it's going to call itself. And finally, we're going to call main down here. Okay, so if I run this, okay, we call this 3.1, no, 12.1, or 12.1. Okay, we'll see this just goes on forever, right, until we stop it. Okay, so we hit C, Control C, there we go. We got it. That's our keyboard interrupt. Okay, and that's the reason that whenever we call message, it calls message again. Okay, so this is called endless recursion or indefinite recursion, something like that. Okay, it will go on until you hit Control C to stop it. Okay, so that doesn't make a lot of sense. What would make more sense, again, we're still just doing relatively trivial examples here to try to make the point, okay, is this one that we're going to pass an argument. Okay, so we're going to pass an argument to message with that tells how many times to print the message. Okay, so we're going to have some stop on this. Okay, it could be whatever they want to send. Okay, it means that we have to receive a variable here. We're going to get an error message. Okay, and then we're going to say if the time is, or times is greater than 0, which means we're not done, we're going to print our message that this is a recursive message. Okay, and we're still going to call message within here. Okay, but this time we're going to call it on times -1. Okay, so the first time this hits, message is going to be sent. Okay, and it's greater than 0, it's 5. So we print it. Okay, it's going to call message again with 4. So instead of calling it indefinitely, it's going to call it with 4, with 3, with 2, with 1. Okay, and in fact, if we wanted to force this issue, we could do a tab there and then do times, just to show that's what's happening. Okay, so let's run this now. And it should be a lot better behaved. Okay, and it's going to go 5, 4, 3, 2, 1. Okay, so we've had a way to restrict what we're doing. Okay, now it's worth talking about what's happening as far as the memory goes. And I'm on the whiteboard with the mouse, which is unfortunate, but we're going to have to make do. Okay, so when we first call our function, okay, so remember, if we have all of the memory, assume these lines are straight and they're not even close, but hey, I'm drawing with the mouse. Okay, if this is the memory we have for the whole program, okay, when we start main, it's going to be in this location. This is main, okay? Then when we call a version of a function, okay, this function, so we have our message function here, the message is there. It was sent a 5. Okay, so another way to put that is that there is a 5 coming to here. Okay. This message function has a call to message, which creates a new version of message. Okay. This time we're going to send a 4. So it's more memory, and it's holding all this memory while we're waiting. Okay. Just put an M there so you get the idea. Okay, message to 4. We have another one that's going to send 3. Okay, and I won't draw it all, but we're going to send a 2. Then we're going to send a 1. Okay, so we have the one that takes the 2 and the one that takes the 1. Okay, when it hits 1, these are all messages, each of these are different versions in all their own spot of memory of the message function. Okay, when it gets to 1 and the next time it's going to send a 0. So it's going to print the message each of these times. Okay. But when it gets to the one where there's a 0, not a room, get the idea, it's going to be false. Okay. In which case they're going to collapse down. Okay. This one's going to go away. Then that one goes away. Then that one goes away. 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 And we're left all the way back at the main. Okay, so I kind of like to think of it as it builds up a house of cards. Okay, and then once it's done, no, I want to be on draw. That's what I want to be on. Once it's done, you're back just to the main in memory. Okay, sorry for the awful quality of those pictures, but hopefully you get the idea. Okay, so it's going to wait until something else happens with that. Okay, so, and again, going back to the code, when it's done, when that's false. Okay, so when, make sure I'm sharing the right thing. Yeah, so when this is false, we just fall out of this function, right? There's no return because it doesn't need to be. We come back to the next line from here. Let me turn on the line numbers. Okay, so after once this hits 0 and line 9 is no longer true, it's going to drop to line 12, which is nothing, so it returns. It's going to return back up to here. Okay, and when it hits here, it's going to go to line 6, and there's nothing there. Okay, so we're done. Okay, so we can even print out here that we're done with recursion. Okay, and if we want to make it more like the book has it, we can get rid of that, get rid of that. Okay, and now when we run it, it should be what we expect. Okay, so we do it 5 times, then we say we're done with recursion. Okay, so when we're thinking about problems that we can solve with recursion, and it sounds in some ways like, what's even the point of this? Okay, we're going to see some examples, which if you're like me is going to make you very excited about recursion. There's a dark side to recursion. I'm not sure if the book mentions it or not. It's that because of all the memory you use, it tends to not be the most efficient way to do things. I think it's very beautiful. I think there are some problems, especially if you go on the next course you'll take is C++ programming, the 1118, but then it's 1180. Then 2180 is data structures. Data structures, a lot of the data structures to get through them, since we don't have all the nice ones built into Python in C++, we're going to use a recursive algorithm. Okay, so there's a lot of reasons for it, but it's not the most efficient way to do things. Okay, so this gets us on to the 12.2 section of the book, and that's on solving problems with recursion. Okay, so the key concept there is that a problem can be solved with recursion if it can be broken down into smaller problems that are identical in structure to the overall problem. Okay, so in the example on the screen there, the problem is we want to print out this message. Okay, we're going to break that up into steps, and we're going to keep calling it recursively. Okay, there are some other problems that we always do when we cover recursion, because it turns out they have a very nice recursive form. Okay, and the one we normally start with is factorial. Okay, so if you remember your math, let me go to the board here so I can write poorly again on it. Okay, so let me clear all this. Okay, so the idea here for a factorial, so if we say 4 factorial, that's a 4 with an exclamation point, is equal to 4 times 3 times 2 times 1. Okay, so in this case, it's 24, right? Arithmetic, remember, it's not good. So it's 4 times 3 is 12, 12 times 2 is 24, okay? So that's what the factorial looks like, okay? So we have to, we can generalize here. We can say that n factorial, okay? So actually, let me do what they're doing. Let's do a more formal thing here. So let me erase that. And let's do that n, if n is equal to 0, that's how they define things here, okay? Then n factorial is equal to 1. Okay, so when we get down to 0, it's equal to 1, just if that ever comes up. Okay, and then if n is greater than 0, okay, then n factorial is equal to 1 times 2 times 3. That's ugly 3. Try it again. Times 3 times dot, 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 n. Okay, so they're going forwards, not backwards. But that's the same basic idea. Okay, so again, to put this in a function form, we can say that the factorial of 0 is equal to 1. Okay, and then the factorial of n is equal to what we have up here. Okay, same basic idea. Okay, so the insight that we need in order to let us figure out this as a factorial or as a recursive algorithm. Okay, so what we're looking for is a pattern that we can divide this into steps. Okay, so the key insight here is that if we're at 4 factorial, it's equal to 4 times 3 times 2 times 1. Well, it turns out that this 3 times 2 times 1 is 3 factorial. Okay, and we can kind of generalize this, and this should be, you should be thinking toward the algorithm here, that n factorial is going to be equal to n times n minus 1 factorial. Okay, so 10 factorial is equal to 10 times 9 factorial. Okay, and this should start to give us the idea of what we just did with the messages, that we're going to be able to call this function repeatedly. Okay, testing to make sure we haven't gone too far, but we can build up the total. Okay, we can return that message. Okay, and this one's going to wait on an answer in the way the other one didn't. Okay, so let's take a look here. The code we have is on page 582. Okay, so let me get off of here, get back to the code. Okay, so I'm just going to wipe this one out. Doesn't matter. We still have the def main. Okay, so for this one, we're going to start by getting a number from the user. And I often don't do this in my programs, but you don't want to get out of the habit. Okay, so the number is, don't know what that did. Oh, it turned up the volume. Okay, number, hit the wrong key, is equal to int, input, enter a non-negative number. Okay. So since we're not dealing with classes anymore, we're back to having to worry about validation. Okay, so the int should tell you we're going to have, and the book doesn't do it, but you should. We should have a try with a value error because int could mess up. Okay, it also means that our function is going to need a precondition. Okay, so we're back to those days now. Okay, So once we have this number, we're assuming for the moment till we get it working that it's okay. We're going to say that fact is equal to factorial of the number that they just typed in. Okay. We're then going to print the factorial of number is fact. I will warn you, these numbers get really big really quick. And while Python won't blow up anytime soon, other languages certainly will. We were in C++. It seems like 100 and something is as much as we can go without blowing it up. Okay. So again, keeping in mind all of the issues that we're going to have to deal with as far as validation, we can go on and do our factorial on a number. Let's call it num down here if you want. Okay. And the two parts that we need, okay, we have to need what we often call, I'm not sure if the book calls this or not, but I know other classes have called this, the base case, okay? It's where we are done, okay? And then we need the recursive step, okay? Which takes the next step. That's pretty self-explanatory, okay? So in this case, the base case here is if the number is equal to 0, okay? So if the number equals 0, we know that that's equal to 1, we're done, okay? We don't have to multiply it by anything anymore, okay? So when that's the case, we're going to return the 1, okay? We know that is a fact, okay? The else is going to contain the recursive step, okay? And this recursive step is going to be that we're going to return the num that we get back times the factorial of num minus 1. Okay. And that's it. I mean, we're going to find that recursive programs are really short, but they're pretty intense as to what's going on. Okay. So just to get us an idea of what's happening here. Okay. So every time we call this, we're going to print f call num. Okay. So we're going to see how many times that's getting called. Okay. We'll see what this does for us. Doesn't like something. Oh, I'm in the wrong language. Don't you hate when you're in C++ when you think you're in Python? There we go. Same thing there. I did pretty good, but this broke me for some reason. Blame the brain fog of the vaccine. Okay, so we're going to enter, that's ugly, we'll fix that. We're going to enter a 5, and we see that we get a function call at 5, at 4, at 3, at 2, at 1, and at 0. Okay. Which is what we wanted. Okay. Is it correct? Well, let's do the one we know. Let's run it again. Unless we've lost our minds arithmetically, which I could. If we do a 4, it should be equal to 24. Okay. Which is what we expect. Okay. And again, it's making the calls correct. So to clean this up, we want to go ahead and do this. Okay. And then we don't need this print statement anymore. Okay. You can keep it back there if you're having trouble. But now when we run it, it should run straight through. Enter a number 4, it gives us the number of 24. Okay. Again, to show that it gets big quick, run it again. Let's say with 100. That's the number we get. That's a big number. That would absolutely blow up other languages. So it's interesting that happens. Okay. But I want us to have an idea as to what this is doing. Okay. As far as the calls go. Okay, so I'm going back, sadly, I know it's unfortunate, to this. Okay, so we're going to clear all drops. I'm making it smaller so I can make it a little clearer. Okay, so if we're in the main function down here, and you call the factorial of 4, let's say, okay? Looking at our code, which, sorry, my Alexa's talking to me. Looking at our code, we're not at the base case, right? It's not equal to 0, okay? So we're going to call 4 times factorial 3. Okay, so actually I do want to make this a little bit bigger. Okay, so this is going to call 4 times factorial of 3. Okay. So the 4 is going to wait. The factorial of 3 is going to be the first time that it calls a version of factorial. Okay. So this is going to have the 3 come up to there. Okay. So this is our next version of this. The 3 doesn't, we're not the base case yet. Okay. So this is doing, in essence, the factorial of 3, which is equal to 3 times the factorial of 2. Okay. And this is all waiting in memory. Okay. That's going to call a version for the factorial of 2. So in essence, we're sending the 2 up to there. Okay. It's going to want to return 2 times the factorial of 1. Okay. So that's going to wait for an answer. We send this up to here with the 1. We're going to do the factorial of 1. Okay. That's going to be 1 times the factorial of 0. Okay. So we call it one more time. We're going to pass it the 0. I'm going to do a factorial of 0, which is the base case. And it's going to say return 1. Okay. When we return 1, hope this erases correctly. When this returns 1, it goes away. Okay. It's going to send it back. All that's gone. Okay. In fact, this fact 0 has now been replaced by a 1. Okay. It can now return a 1 by 1. Okay. So this 1 by 1, now this gets torn down. And the 1 by 1 going to replace with a 1 here. Okay. Well, that was waiting, but now it has what it needs. So it's going to return 2 times 1 or 2. Okay. So this goes, and this call gets replaced with 2. Okay. So now fact 3 we can figure out is 3 times 2, which is 6. Okay. So again, all this goes away out of memory. And all of this gets replaced with the 6. Okay. Which now it returns back to main the 24. Okay. So that's the idea. Okay. So at one point, all of this is in memory, okay, which is why it's not super efficient. So let me back up that more. So we built that whole structure up all the way until we get to the base case. We're now at the base case. We can now get rid of things, okay, go back to the main, okay? So that's the idea. So that's what's going on in this code. Okay, so we'll go back to the desktop. That's what this code is doing. Okay. The other example that we always do with the Fibonacci's And this last section gives some examples, and we'll do at least a couple of these, okay? The first one here is going to be the Fibonacci series. Oh, actually, that's going to be the second one. First one going to be here is going to be summing the range of list elements with recursion. Okay, it's a different one. We don't see this one as much, so let's do this example. Okay, so this is 1214 on page 585. So this one we're going to create numbers be equal to the list 1, 2, 3, 4, 5, 6, 7, 8, 9. We could have used a range as well, but let's do it that way like the book did. Okay. Then we want to get the sum of the items at indexes 2 through 5, for example. Okay, so we can say my sum is equal to range, numbers, comma 2, comma 5. Okay, so we're doing our own range here. Okay, then when that's done, we're going to put, oh, and on the last program, I didn't go back and add the try or the preconditions, but I should have. Okay, if I do this live in class, I'll do that for sure. Okay, so this one we're going to display that the sum of items 2 through 5 is my sum. Okay, and this should be not range itself, but range sum is the function we're writing. Okay, so we're going to define our range sum function. Okay, it's going to take a number list, it's going to take a start, and it's going to take a stop. Okay. We're going to start with our base case, okay? So if the start is greater, they've actually got start and end, not start and stop. It wouldn't matter, but let's keep it consistent with the book. If start is greater than end, then we've passed ourselves, basically, okay? And we know that we're at the base case. So this is the base case. Okay. In which case, we're just going to return a 0. There's nothing new at that point. Okay. Then we have our else, which is going to be our recursive step here. Okay. That we're going to return num list start. That's what we're saying the function as. Plus the range sum that we're going to send it, the num list, still we have, with the start plus 1 and the end. Okay, the end stays the same, but the start's going to go up every time. So in our example, we start at 2 the first time, they're going to go to 3, then 4, then 5, and then 6. When we're at 6, the start is bigger than the end, and we're going to return that. Okay. But if not, it's going to return itself back to be added up. Okay. So that should be all we need there. Let's run this one. Doesn't like something. What does it not like? I don't know what it didn't like. Oh, someone else had this problem. It doesn't like something above. You got to keep looking at the line before. Let's see if that fixed it. There we go. Sum of 2 through 5 is 18. Okay, so that should be 2 plus 3 plus 4 plus 5, basically. Just 5. Yeah, looks like it should be okay. Although I guess it's 0, 1, 2. So it's 3, 4, 5. Yeah, it's 3 plus 4 plus 5 plus 6 is 18. Yeah, I think we're good. Okay. So that's another example of using recursion. On this one, we don't really have too much to, I guess we do need to have some preconditions here. Okay, we have the preconditions that num list is a list, start and end are integers. Okay, and we can do the is instance to check those. Okay, we don't need a try here. Well, yeah, we do. We need a try. So I guess up here we would have to do a try, and our accept would be on the index error because we're using a list. Okay, that's all we're doing there. Okay. In fact, let's go ahead. Let's just do this. Let's not just say we're going to do it. Let's do it. Oh, that's our preconditions. Okay, so we can say here, if not num list is instance, num list list, we can return -99, whatever you want to do. And then if not is instance start int return -99. There's probably a way to do this all at once, but like before, it's not worth the mental effort to do it. And int return -99. Okay, so all that's the precondition. The rest should work pretty straightforward. Okay, again, we don't need the try down here because if this error happens here, it's still going to flow back to there. Okay, we just need it one place. Okay, so that's another example of a recursive function. Okay, the one I thought they were doing next, which they're not, is the Fibonacci series. Okay, which is an amazing series that you should know something about if you don't. But it's basically that it was invented by this guy, Leonardo Fibonacci. He was born in 1170, so a long time ago. And with this, the series is we start with 0, 1, 1, and then we create each additional series by adding the first two together. Okay, so we have 0 and 1 is 1, 1 and 1 is 2, 2 and 1 is 3, 3 and 2 is 5, 5 and 2 is 8. Sorry, I said it, I didn't type the right one. 5 and 2 is 8. And then we go to 13, then we go to 21, then 34, then 55, and so on. Every time it's the previous two numbers added together. Okay. And it turns out that this really is quite useful in areas where you wouldn't imagine. Things like if you count the number of petals on the outside of a flower, a complex flower, that Fibonacci number of the series or that member of the series will be the total number of petals and all kinds of crazy things. Okay. So this is a little different than we were doing before in that we're going to go through and do two things are going on. We're doing a double recursive call in essence. Okay. So let's go through this. Okay. So we're going to print out here a message. The first 10 numbers in and they break this for some reason, print Fibonacci series. Someone's names are going to capitalize it. R. Okay. I'm going to say for number in range starting at 1, going up to, but not including 11, so 1 to 10, we're going to print the fib of that number. Okay. So then we have to define our Fibonacci number. And I didn't put it down, but on this one, we've got if n is equal to 0, the fib of n is 0. If n is equal to 1, the fib of n is 1. Anything else? Let's go ahead and, this is something we should put in a comment. Okay, so we're going to assume that the fib of 0 is equal to 0. The fib of 1 is equal to 1. And then the fib of n greater than 1 is going to be equal to the fib of n minus 1 plus the fib of n minus 2. Okay, so we have multiple versions of this floating around at the same time. It's going to take up a lot of memory. Okay, we should have plenty. If we get really big numbers, it shouldn't be a problem. Okay, so down here, we're going to take the n that comes in. In this case, we have two base cases, right? The base case is where we know the answer. They're what up here just happened immediately. Okay, so down here we can say if n is equal to 0, that's a base case. We're going to return 0. We know the answer of that. Okay. Else if n is equal to 1, we also know there we're going to return a 1. Okay. Else, now we're going to have our recursive step. Okay. What we're going to return is the fib of n minus 1 plus the fib of n minus 2, just like we were doing up here. Okay, we're copying line 4 verbatim. Okay, that's all we should have to do. We should be okay. Okay, so we're going to grab a number from here. The first time through, the number is going to be 1. Okay, so it's going to return a 1, print a 1. We're done. Okay, the next time 2 is going to be a 2. Okay, so it's going to go to this one, and it's going to say return here the fib of 2 minus 1 or 1. Okay, and it's going to make a call to the fib of n minus 2 or 0. Okay, so the fib of n minus 1, okay, is going to return the 1. The n minus 2 is going to return a 0 right away. It then returns the 1 plus 0. It's going to give us a 1 for there too. Okay, the next time through, when we're at 2, okay, it's going to create, and you're going to see the tree here pretty quickly. When we're at 2, it's going to give us the fib of 1, which we know. No, I'm off 1. Okay. No, it's the third number. There we go. Anyway, when I get the next one, I'm going to have to calculate. So when we're at the last one, we're at the fib of 10 here, the 10th number. Okay, that's going to be the fib of 9 plus the fib of 8. But the fib of 9, we have to do the 8 plus the 7, and then the 7 plus the 6, and then the 5 plus the 4, or 6 plus the 5, 5 plus 4. All this goes on, okay? Which gets pretty crazy as we're doing it, okay? And we can kind of keep up with that if we want. We can put in a print. So we're going to put in a couple of stars here, and then we're going to put in every time we do that. Okay. So let's see what we're going to get. Should be interesting. Unless I've got a typo, which is very possible, as you know. Yeah, there we go. The last thing it should give us should be a 55. We'll see. Yeah, that's 55. Okay, but look what it did. This is where the inefficiencies come in. So just between the 34, we do a 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 1, 2, 1, 0, 3, 2, 1, 0, 1, 4, 3, 2, all that. All that's happening at once. Okay, we're basically creating this tree every time we do it. Okay, and we end up calling the same thing over and over. Okay, so just in this instance, we've got there's a 0, there's a 0, there's a 0, there's a 0, there's a 0. We're not even done. All those zeros. Not very efficient, okay? But it is kind of cool. It is straightforward enough to do, and it is going to give us the correct answers. Okay, so there we have it. Okay, so the last problem in this chapter that we're not going to go through, if I do this in class tomorrow, we will. It's the Towers of Hanoi problem, which has a recursive solution. You should look through that. It's on page 588. Okay, but it's more than we have time. We're already at 42 minutes for the video. Okay, So the last section there talks about, it's a short section, but it's worth thinking about, the recursion versus looping, okay? Any algorithm that can be coded with recursion can also be coded with a loop, okay? So you can always do a loop version, okay? And it would be interesting. There may be a homework problem. I don't know. I haven't assigned homework yet, but it'd be interesting to look at like the Fibonacci to look what a loop-based version would look like, okay? We know we can always do it, okay? You never need to do recursion, okay? So there are several reasons we shouldn't use recursion, okay? And the book says it. So they do talk about this, which is good. And we just saw the massive inefficiencies there. So it's certainly less efficient. So each time a function's called, the system incurs the overhead that we don't have to do with a loop. A loop doesn't have to allocate memory every time it goes through the loop. So the most things we do, most of the repetitive programming we do are better with a loop, okay? We don't need to look for recursive solutions when they don't need to, okay? But some problems are more easily solved with recursion than with a loop, okay? An example of that is the greatest common divisor, which it actually did. So if the recursive solution is evident for a particular problem and the recursive algorithm does not slow system performance an intolerable amount, then we can do the GCD. I actually wanted to look at the GCD. Some of they do, and I forgot it, okay? So that's the last thing we're gonna say about that. But let's go ahead and do this GCD program as well. You know me and math, I like math. Okay, so let's take a look at this one. So on this one, we're going to, it says get two numbers. I'm just gonna flat plug them in. Video's getting long already. Be curious if anybody gets to the end here. So let's say we're going to do a 56. Let's say that a num2 is equal to 33. Okay. I'm going to print GCD is the GCD function we're going to create of num1 and num2. Okay. All we're going to do, we're keeping it simple. So we're going to define this GCD with an x and a y to come in. Okay. Our base case here is if x mod y is equal to 0. Okay, what does that mean? It means that x divides y and there's no remainder. Okay. If that's the case, we're going to return y. Okay. We're done. Okay. Or else then, our recursive step then is to return the GCD of x and x mod y. Okay. So yeah, this is based on the definition, the way it works with remainders and all that stuff. Okay. So let's see if this works. I don't know what the answer for that is. We'll see. Okay, it didn't go on forever. Looks like a 2. 2 does not look correct because 2 is not a factor of num2. So I'm doing something incorrect. Okay. If x mod y is equal to 0, return y, else return GCD of x mod y. That's really weird. I don't know why. I think there's a, I can't do it, that's got something else. I think there's a GCD function built into the math library. Let's see if there is. If I find my home keys, I should be able to print math.gcd of num1, 2. Okay, looks like I'm going to get a different answer, which is really strange. I have to work that one out. Oh, I've changed my name, so I have to change it here. I had to change the name of the function, or it would have ran the local version and not. Oh, with it saying the math thought it may have ran the other way, but we'll be on the safe side. Yeah, it should be equal to 1. I'm off somewhere. Oh, not sure. Yeah, I have to spend some time figuring that out because I've got exactly what they've got. The GCD of xy, if x mod y is equal to 0, return y, else return GCD x comma x mod y. Yeah, don't know why it's not working. Very strange. But that's what the book has, and apparently the book's on. So I'll have to figure that one out. In any case, it does show the recursive aspect. We're going to keep going until we get the correct answer. Okay. So that's it for recursion. Hopefully I'll be in class tomorrow and we'll be able to talk about this. But if not, you'll have this video, and you'll have this video anyway, because I'm going to release a video no matter what. Okay. If you have questions on any of this, make sure that you let me know, or just watch the video again.